Hello, and welcome to our video on L2 convergence of Fourier series and some philosophical discussions thereof. Here is what we learned last week. If you have a function on the interval minus p to p into the complex plane, and this function is integrable, then the Fourier coefficients f hat of k are defined for all integers k. In this video, I will just use the complex Fourier coefficients f hat. Of course, we can also talk about the real coefficients ak and bk. So we know how to define the Fourier coefficients, and we know how to calculate them. We have practiced doing those integrals and using our formulas. And so the Fourier series for f at a point x makes sense as a formal series in the complex plane. We can write down the coefficients and all the terms in this series, just like we would have a series back in calculus, and then we can wonder about its convergence. So the questions are, does the Fourier series for f at x converge as a series in the complex plane, given a number x? To what does it converge? What is the sum or the limit of that series? Does it converge to anything resembling f of x, the function and the pointwise value we started with? We saw that we have a result that if f is piecewise continuously differentiable, then the Fourier series for f at x does converge for all points x in the interval minus p to p, and there is a formula that relates the sum of that series to f of x. It's not necessarily f of x precisely, but we can pull f into there. And that was our theorem 2.4.12 in the current indexing in the lecture notes. Okay, not bad. So the function's piecewise continuously differentiable. Then we can talk both about the fact that yes, its series converges, and we know what it sums to and how to relate that to f. But what if our function f is not piecewise continuously differentiable? This is, although it may not seem like it from the point of view of calculus, kind of a strong restriction on f, being piecewise continuously differentiable. A function, it turns out, can be discontinuous at a countably infinite number of points, at a sequence of points, xk, indexed by k equals 1 all the way up through infinity, in the interval minus p to p, and still be integrable on minus p to p. If you're discontinuous at infinitely many points, you can't be piecewise continuously differentiable per our definition, so theorem 2.4.12 doesn't apply to you. But it's still possible, though not always guaranteed, that when you're discontinuous at infinitely many points, you're still integrable. So that means your Fourier coefficients are still defined, you still have a Fourier series. In fact, we can even dig up a pathological example, or non-example since I don't quite give you a formula for this. If you give me a countably infinite set xk from k equals 1 to infinity in the interval minus p to p, you can find a continuous function f on the interval minus p to p, such that the Fourier series for f at these points xk diverge as series in the complex plane for all k. So what does this mean? Even being continuous on the interval, not continuously differentiable, but just continuous, doesn't guarantee that your Fourier series converges back to f, or that the series converges at all. And yet, if you have a continuous function, it's definitely integrable, so it makes sense to talk about the Fourier coefficients of that function. So weakening from piecewise continuously differentiable to just plain old continuous can destroy the convergence of a Fourier series. And so we're led to ask, what can be said about the convergence of the Fourier series of a function that's just integrable? After all, if you're integrable, you have a Fourier series, but who knows if it converges? So let us do the classical thing in math when a question is hard and confusing. Let's give up and ask a different question. Another good question to ask, rather than does the Fourier series converge at a particular point, does it converge back to f, is rather, how do the partial sums of an integrable function's Fourier series approximate that function? Do they give a good approximation to that function? And I'll use the notation throughout this video. Sn on f at x is the sum from k equals minus n to n of f hat of k times e to the ik pi x over p. So this is the nth partial sum of the Fourier series for f, and I'm just writing it in the complex form for my convenience. Ideally, in the most perfect of worlds, you would have the limit as n goes to infinity of Sn on f at x equals f of x for all x, and we know this is most certainly not a perfect world, so we cannot expect that to happen all the time. Or maybe it would equal something involving f of x in a slightly imperfect world. But that's not going to happen. Realistically, the best we could hope for is that Sn on f is a good approximation to f on the interval minus p to p. So what could we mean by good approximation? How could we define that and how could we achieve it? When is one function on average, or overall, a good approximation to another? If we're thinking about how two functions, in this case Sn on f and f, relate to each other over the interval minus p to p. Well, one way to think about this would be to say that a function's on average a good approximation to another one when the average value of the difference between those functions is small. Really, when the average value of the absolute value of the difference between those functions is small. So what do we mean by average value of a function? Going back to calculus, we know that the average value of a function g from the interval a to b into the complex plane is the number 1 over b minus a times the integral from a to b of g. And if g is piecewise constant, you'll see in the exercises, this literally gives you back the average of a bunch of numbers.